Nth roots, radicals, and exponential functions, day 2. So let's talk about our properties. So as a reminder, we can have an nth root, which is here on the left-hand side, and two different bases underneath. It could be an x and a y, it could be an a and a b, it could be a number and a variable, and we can split it up as long as it remains under that same root. So nth root, 8th root, 5th root. We can also do the reverse. We can be given bases that are separated and put them together. So just be aware that these properties work in both directions. Now remember, we can switch between radicals and exponentials. So the properties are the same. If we have an exponential on the outside of two different bases, a and b, then that means that we can apply that exponent to both a as well as b. And also vice versa. If we have two different bases and they both are raised to the same exponent, we can condense them and put them together. Our quotient property means that we can have a radical and then a and b underneath, and we can separate it into two different radicals. The thing you have to know, though, is that when something is fully simplified, you cannot have a radical in the denominator. So we'll talk about that a little bit later as well. And for our exponent rules, remember, if we have an exponent on the outside, it applies to both the numerator as well as the denominator. So take a moment and make sure you write these rules down. So here's our first question. We are going to rewrite the product, or the quotient, in this case it's a product, of the radical. So we have two different radicals, but both have the 5th root. So if we go back to our rules, we have this situation. So what we're going to do is we're going to simplify by putting both radicands underneath the same radical. And when I say radicand, I'm talking about the 16 and the 8. So I'm going to make a 5th root, and I'm going to put 16 times 8 underneath it. Then I'm going to actually do that math. So I'm going to change that to be 128. Can I actually simplify that? Now remember, the only way that we can cancel a 5th root is if we have something raised to the exponent 5, because then we can cancel these out and we're left with whatever we had underneath here. So that means we're looking for a factor of 128 that can be raised to the 5th. Well, 128 can be broken down into 32 times 4, and why 32 is important is because 32 is the same as 2 to the 5th. So I'm going to change this to be 2 to the 5th times 4. Both are still under that 5th root radical. Now I'm going to separate these radicals again. So if I go back to my rules, I'm here and I'm going to separate them. So we have the 5th root of 2 to the 5th, and then we have 4. So I'm going to separate these. These are going to cancel, so we're left with 2, and we cannot simplify the 5th root of 4, so we leave that. And our solution is 2 and the 5th root of 4. Now we're going to rewrite another one. What's challenging here is notice that we have a 6 and a 3 with our radicals. So the first thing we have to do is figure out how to make those the same. So we're going to change this into exponential form. So I'm going to change this to be 8x to the 1/6. Now what's important here is that you put parentheses around the 8 and the x, because both the 8 and the x are underneath the radical. So that means that the exponent of 1/6 has to be able to attach to both. Then we have that multiplication sign, and we have 2x to the 1/3. We need a denominator that's the same. So we're going to change 1/3, and we're going to change that to be 2/6 because those two are equivalent. So I'm going to rewrite this. Now we're one step closer, but unfortunately, if we go back to our rules say that we have to have the exact same exponent on the outside, and we don't. We have 1/6 and we have 2/6. So what I'm going to do is I'm going to create a power to a power rule on the second term. So I'm going to take the 2x and I'm going to raise it to a 2, and then that entire thing is raised to the 1/6. So if I was going to multiply these exponents together, we would end up with 2 times 1/6, which is the same as 1/3. So all we've done is modified the question. Now, I would never expect you to know to do this other than the fact that I am now showing you a strategy. So if you're sitting there thinking, how would I ever know this? You wouldn't. And that's okay. So I'm going to highlight 8x and 2x squared. And the reason I'm doing that is to show you and emphasize that both are now raised to the same exponent. So let's go look at our rules. So when we have two bases that are raised to the same exponent, we can condense them and put them together with that same exponent on the outside. So that's the rule we're going to use right now. So I'm going to keep that 1/6 on the outside, and on the inside I have 8x, which I get from here, and then I have 2x squared, which I get from the second term. I'm going to focus on the inside now. I'm going to keep that 1/6 on the outside, and I'm going to change this to be 8x times 4x squared. So I'm applying this exponent to both the 2 and the x. Then I'm going to simplify. So 8 times 4 is 32. X times x squared, the bases are the same, so I add the exponents. The next thing I'm going to do is I need to put it in reduced radical form. Well, I'm in exponential form right now. So I'm going to change this back to a 6th root of 32 x to the 3rd. Now the reason why this is the final answer is in order to cancel my x's, I need 6 of them because I have a 6th root on the outside. And in order to simplify that 32, I need a number that simplifies to have a power of 6. Well, we know that 2 raised to the 5th is 32, not 2 raised to the 6th. So that means that this is our final answer. Now we're going to look at the quotient. If we go back to our original property, when we have a radical, we can split it into a denominator and a numerator. So that's the first thing we're going to do. The next thing I'm going to do is I'm going to simplify that denominator. So this is the same as 3 squared and m, and then the numerator is going to stay the same. Now the reason why I did that was I want to show you that we need another 3 in the denominator and 2 more m's in the denominator. And the reason that we need another 3 and 2 more m's is because then we would have 3 3's and 3 m's. And why we want to have 3 3's and 3 m's, if we had 3 3's and 3 m's, then that means that we could actually simplify the radical. So the cubed root would cancel with the 3, and the cubed root would cancel with the other 3 on the m. So we would be simplified and we'd be left with 3m. So what we're trying to get to in the denominator is 3 cubed and m cubed. So to get there, we're going to multiply the top and the bottom. by a 3 and 2 m's. So just look at the denominator right now. As long as the radicals are the same, which they are, that means that we can multiply what's underneath together. So we can multiply that 3 squared with the 3 together, and we would end up with 3 cubed. Bases are the same. We would add the exponents. Look in the denominator again with our m's. We have 1m. When we multiply that with m squared, we have m cubed. So the denominator is exactly where we want it, because we just showed on the right-hand side over here that that would simplify to be 3m. If we're going to insert a cubed root of 3m squared, whatever we do on the denominator, we also have to do in the numerator. Now the last thing we need to do is multiply the numerators together. So they're both under a cubed root, so we multiply the 2 and the 3 together. That gives us 6, and because the one is m squared and then n, we can't simplify those and put them together. So in the denominator, that cubed root and cube will cancel, and the cubed root and the cube will cancel. In the numerator, there's nothing to cancel. We don't have any factors of 6, we don't have 3 m's, and we don't have 3 n's. So the numerator will stay the same. Now this is just an introductory look. If you don't know how to do this at this point, it is okay. It's just something that you can review and look back at.